Our topic today is transformation of functions. So in transformations, the first transformation is translation. Without changing the shape or size. First is vertical translation. For vertical translation, the most basic example will be of the graph y equals x square to x square. Now, if we translate this by 2 units upwards, the y-intercept will change. This point will be, this is the vertical translation. And now, if we want to write this in terms of fx, the equation would be fx plus 2. Next is the horizontal translation. Again, I'm taking y equals to x square. This is x. Now, for example, we have to translate this horizontally by 2 units towards the left. So now the x-intercept will change. This point will be -2. If we have to write this in terms of fx, so this will be fx plus 2. So what you have to note over is that in horizontal translations, if it is moving towards the left, then we'll have a positive sign. And if it is moving towards the right, then we'll have a negative sign. So if, for example, it was shifted by 3 units towards the right, that means the x-intercept would be 3. The equation for this in terms of fx would be fx minus 3. Achha, now why is that? Example, again, I'm taking the same graph of y equals to x square, and then it's being translated towards the right by 4 units. So the first equation was y equals to x square. And the second equation will be fx minus 4. So that means that we're replacing x by x minus 4. So this is x minus 4 whole square. Now, what we know by the graph is that the x-intercept has to be 4. Matlab ke at 4, the value of y should be 0. Now over here, if you input 4, you will get 0. But if, for example, you wrote the equation of this translation as x plus 4, then when you would substitute x by 4, the value should be 0, but it's coming 64. So when we're translating horizontally, If we're translating towards the right, then we'll have a negative sign, and if we're translating towards the left, then we'll have a negative sign. Positive sign, sorry. So this was the vertical translation. So if we want to show the vertical translation in terms of vectors, the vector is 0 and C. 0 represents that 0 shows that there is no change in the x values, and C shows that there is a change in the y values. And we can also write this as fx plus C. So if C was negative, then it would go downwards. If C was positive, it would go upwards. In horizontal translations, we can write them as fx plus C, and in vector form, this would be minus C 0. So if, for example, we had negative C, for example, negative 2, if we had x minus 2, then that is showing that the translation is towards the right because it's a negative sign. So in the vector, it would be 2, 0, which means that x is going towards the right by 2 units and y is unchanged. Next is reflections. In our syllabus, we have reflections in the x-axis, in the y-axis, and in the line y equals. So first, in the x-axis, in reflection of the x-axis is acting as a line reflection. I'll again take the graph of y equals to x. This is fx. Now, after reflection in the line, in the x-axis, every become negative. So this will be the reflection. And if we want to present this in terms of fx, it will be f negative x. Next is the reflection in the y-axis. Here, the y-axis acts as the line of symmetry or the line reflection. So, for example, we have to reflect it in the y-axis. This is also called horizontal reflection. So, take this point. We'll take this point and translate it horizontally. And this distance should be equal to this distance. This point will stay the same as it is an invariant point. That is, it is on the line of reflection. And this will also be translated horizontally. And this distance will be equal to this distance. So this is the reflection in the y-axis. And over here, if this is fx, then the red line is f negative x. Third is the reflection in the line y equals to x. This usually does not come under transformations, but we've done it in inverse functions. Inverse functions are the reflections of each other in the line y equals to x. So in the reflection in y equals to x, fx is converted to f inverse x. What is an even function? An even function is when fx is equals to f negative x. This means that in an even function, the reflection in the y-axis produces the same function again, which means that the y-axis is a line of symmetry of the function. For example, if we have example that we're taking earlier, y equals to x square. Y equals to x square is an even function. because if we reflect it in the y-axis, the reflection will be the same as the original equation. Now, what is an odd function? In an odd function, f negative x equals to negative fx. This means that the reflection of the function in the x-axis is the same as the reflection of the function in the y-axis. For example, the function of the cubic function x cube this is the graph for x cube. Now, if we reflect it in the x-axis, that is the vertical reflection, the vertical reflection will produce this kind of shape. And if we reflected, if we reflected the same function x cube in the y-axis, it would produce the same result. So this is an odd function, and the property of an odd function is that it has rotational symmetry of order 2. Because if we rotated this, it would fit into the same shape after 180 degrees. The next transformation is stretch. There are two types of stretches. The first is the vertical stretch. So in the vertical stretch, I'll take the example again of a quadratic function. For example, this was the graph. In the vertical stretch, the x-axis is the invariant line and the y-axis is parallel to the stretch. Which means that we can call it a stretch parallel to the y-axis with invariant line x-axis, or we can call it a vertical stretch. So for example, on this line, we had 3 points given. This is 2, 4. This is negative 2, 4. And this is 0, negative 4. So if we applied a stretch of stretch factor 2, then every point on this graph, the distance of every point on this graph from the x-axis would be doubled. So for example, this distance would be doubled. This point would move upwards. This distance would be doubled. The point would move upwards. And this distance would also double. The point would move downwards. So the new coordinates would be, in the new coordinates, the coordinate of x would be the same, but the coordinate of y will double. So over here it will be 2, 8. And over here it will be minus 2, 8. And over here it will be 0, negative 8. This will be the vertical stretch. Now, if we had to show this in terms of fx, so if the original function is fx, after the vertical stretch, the function would be a times fx, where a is the stretch factor. Next is the horizontal stretch. In the horizontal stretch, the y-axis is invariant line and it is parallel to the x-axis. Here I'm taking the curve y equals to x square. So taking any 2 points on the curve, this point is 2, 4, and this point is negative 2, 4. Now, if we apply a horizontal stretch with stretch factor 3, every point on the distance of every point on the curve from the y-axis will be multiplied by 3. So, for example, the distance from the y-axis till this point is 2 units. Now it will become 6, and the coordinates will be 6, 4. For this point, again, the distance will be tripled. It will become 6, and the coordinates will be minus 6, 4. This will be the graph for the after the horizontal stretch. And over here, if the original equation was fx, after the horizontal stretch, the equation will be f1 upon ax, where a is the stretch factor. You'll have to learn this, that in the horizontal stretch, always when we're writing it in terms of fx, the stretch factor is divided by 1. If, for example, the stretch factor was 3, then fx would be converted to fx upon 3. And if, for example, the stretch factor was 1 upon 3, then fx would be converted to f3x. Now, the next part in transformations is combined transformations. If there are two vertical transformations. Now, what are vertical transformations? Vertical transformations are vertical translation, vertical stretch, or vertical reflection. That is reflection in the x-axis. These are the three vertical translations. If we have two vertical translations being applied together, then we follow the order of BODMAS. That is, we first multiply or divide and then we add. So for example, if we have 2fx plus 6, first we'll apply the 2. First we'll apply the 2. That is the vertical stretch, because first we multiply or divide and then we add or subtract. And after that we'll apply 6. That is the vertical translation upwards. If we have two horizontal transformations, then we follow the reverse of the general BODMAS. That is, we first add or subtract and then we multiply or divide. So for example, if we have f2x minus 3, then we'll first over here we'll first add or subtract and then we'll multiply or divide. So we'll first add or subtract. That means that we'll first apply this horizontal translation, that is towards the right by 3 units. And then we'll apply this horizontal stretch, that is with scale factor 1 upon 2. Now, for example, if we had f negative 2x, or if we had negative 4fx, over here we have two horizontal translations, but because both are being multiplied, so the order won't matter. We can either first apply the horizontal reflection or the horizontal stretch. And over here there are two vertical transformations. And again over here, because both are being multiplied, the order does not matter. So we can either first apply the vertical translation, vertical reflection, or the vertical stretch. Now the third case is when there is one vertical and one horizontal. In this case, the order does not matter. We can apply whichever we want first. Now we'll do a few questions of these transformations. So first I'm doing question 6. The graph of y equals to x square minus 4x plus 1 is translated by the vector 1, 2, and we have to find the equation of the graph after the translation. So over here, there is one vertical and one horizontal. So the order does not matter. We can either apply the vertical first or the horizontal first. So I am first applying the vertical transformation. In the vertical transformation, the notation is fx plus c. So over here, it will be fx plus 2, as 2 denotes the vertical translation. So this will become x square minus 4x plus 1 plus 2. This will become 1 plus 2 will become 3. So this is the graph, this is the equation after the vertical translation. Now we'll apply the horizontal translation. So for horizontal translation, the notation is fx plus c. Over here, fx plus c, and the vector form is minus c0. Over here, for the horizontal, the vector is 1, 0. So that means that c will be -1. So we can write this as fx minus 1. So in this equation, we'll substitute x minus 1 in place of each x. So this will become x minus 1 square minus 4x minus 1 minus 3. So this will become x square minus 2x plus 1 minus 4x plus 4 minus 3, that is equals to x square minus 6x plus 2, I think. So this will be the equation after the transformation 1 with after the translation with vector 1, 2. Now over here, this is for reflection, and I'll be doing parts A and B. So for part A, x square plus 7x minus 3 is being transformed to minus x square minus 7x plus 3. Now in these type of questions, we have to observe the change in the equations. So over here, we can see that if you multiply the first equation, by -1, it will become negative x square negative 7x plus 3. And this is the resulting equation. So this means that the transformation is a reflection in the x-axis, that is a vertical reflection. Now in part B, again, we have to observe the change in the equations. The first equation is x squared minus 3x plus 4, and second equation is x squared plus 3x plus 4. Now, we can see that if we replace each x by negative x, we'll get the resultant equation. So in this equation, I'm replacing each x by negative x, which means that it's a horizontal deflection in the y-axis. So if I replace each x by minus x, the result will be x squared plus 3x plus 4. That is the equation that we were given. So that means that in the second part B, the transformation was a horizontal reflection in the line in the x-axis. Now from here, I'll first do part A. So again, in these type of questions, we have to observe the change in the equation. In the first one, we can see that if we multiply this equation, okay, so over here, if we replace each x value by 2x, so that means f2x. So we'll try that. 2x whole square plus 2 times 2x minus 5. This will become 4x square plus 4x minus 5, which is the equation given. So this means that there has been a horizontal stretch that is parallel to the x-axis, invariant line y-axis, with scale factor 1/2. The next one will be part B. In part B, if we multiply the first equation by 3, so it would be 3x square minus 9x plus 6, which is this given equation. This means that we multiplied the equation by 3, that is, we transformed it to 3 times fx. This means it is a vertical stretch with scale factor 3. Now, how do we observe that? Will it be horizontal or vertical? If the constant is not changing after the stretch, then it has to be a horizontal stretch, as in the horizontal stretch, only the x values are affected. However, if the constant is changing, as in b, then it will be vertical, as in the vertical stretch, all the terms are multiplied by the stretch factor. Now, the next question I'm doing is 7. So in part A, it's asking that determine the sequence of transformations that maps y equals to fx onto each of the following functions. Now, we learned that in vertical transformations, we first apply the we first apply the transformation which is being multiplied, and then the one which is being added. Over here, this half is being multiplied. Half represents a stretch by stretch factor half, sorry. So first we'll apply the stretch, the vertical stretch with stretch factor half, and then we'll apply this vertical translation of 3 units upwards. In part C, there are 2 horizontal transformations. In this case, we first apply the one which is being added or subtracted, and then we apply the one which is being multiplied or divided. Over here, -6 represents a horizontal translation of 6 units towards the right. We'll apply that first. After that, this 2 represents a horizontal stretch with stretch factor half. So first we apply the horizontal translation and then the horizontal stretch. Now I'm attempting question number 9. In question number 9, we have been given the function fx as under root x. Now first they're applying a reflection in the x-axis. So after the reflection in the x-axis, it becomes negative x. So we'll have negative fx, that is equals to negative root x. Then there's a translation of 3 units. This is vertical, as it represents the change in the y coordinates. So it is 3 units upwards. So we'll have negative root x plus 3. Then there is a translation that is horizontal of 1 unit towards the right. That means that we'll have fx minus 1, fx minus 1. So we'll replace x with x minus 1. So it will become negative under root x minus 1 plus 3. Lastly, we have a stretch parallel to the x-axis with stretch factor 2. This means that if it is parallel to the x-axis, it is a horizontal stretch. And if the stretch factor is 2, we'll multiply x with half, as the stretch factor is 1 over a. So over here, we'll have negative root x upon 2 minus 1 plus 3. Now in part B, again, the equation given in the beginning is root x. First, there's a translation of 3 units. This is vertical, so root x plus 3. Then there is a stretch parallel to the x-axis, again a horizontal stretch, and stretch factor is 2. So we'll replace x by x upon 2. This will become root x upon 2 plus 3. After that, there is a reflection in the x-axis. That means that fx will be transformed to negative fx. So everything will be multiplied by minus 1. It will become negative root x upon 2 negative 3. Lastly, there is a horizontal translation of 1 unit towards the right. So x will be replaced by x minus 1. This will become negative root x minus 1 upon 2 minus 3. Minus 3 is outside the root.